Hi all, I am K. Surya working as assistant professor in the department of ECE at SNS College of Technology. In this video, let us see about magnitude comparator. A magnitude comparator is a combinational circuit that compares two digital or binary numbers in order to find out whether one binary number is equal, less than, or greater than the other binary number. We logically design a circuit for which we will have to input one for A and the other for B and have three output terminals, one for A greater than B condition, one for A equal to B condition, and one for A less than B condition. These comparators are used in digital systems such as for sorting networks and decision-making circuits to handle numerical components perfectly without any error. The circuit works by comparing the bits of the two numbers starting from the most significant bit and moving towards the least significant bit. At each bit position, the two corresponding bits of the numbers are compared. If the bit in the first number is greater than the corresponding bit in the second number, A greater than B output is set to 1 and the circuit immediately determines that the first number is greater than the second. Similarly, if the bit in the second number is greater than the corresponding bit in the first number, A less than B output is set to 1 and the circuit immediately determines that the first number is less than the second. If the two corresponding bits are equal, the circuit moves to the next bit position and compares the next pair of bits. This process continues until all the bits have been compared. If at any point in the comparison, the circuit determines that the first number is greater than or less than the second number, the comparison is terminated and the appropriate output is generated. If all the bits are equal, the circuit generates an A equal to B output, indicating that the two numbers are equal. There are different ways to implement a magnitude comparator, such as using a combination of XOR and an OR gates, or by using a cascaded arrangement of full adders. The choice of implementation depends on the factors such as speed, complexity, and power consumption. So this is the block diagram of a comparator where you have two inputs A and B and three outputs A greater than B, A equal to B, and A less than B. So the truth table of a 1-bit magnitude comparator is shown here. Since it's 1 bit, A will be 1 bit and B will be 1 bit. So as shown here, and 0 and 0 combination, both A and B are equal. So A equal to B output is 1. If A is 0 and B is 1, A is less than B and so A less than B is equal to 1. And if A is 1 and B is 0, A is greater than B and A greater than B output is equal to 1. And if A and B both are 1, then A equal to B is 1. So using this, the expressions are generated here. So for A greater than B, only one of the output is 1, which indicates A B bar. And for A less than B, again only one output is 1 and it indicates A bar B. And for A equal to B, two outputs are 1, which is A bar, B bar, and AB. So the expressions are for A greater than B, it is A B bar. For A less than B, it is A bar B. And for A equal to B, it is A bar B bar plus AB, which indicates an XNOR gate. So the logic diagram for this is shown here. So for A greater than B, A less than B, and A equal to B. So XNOR gate is nothing but a not operation of an XOR gate. Um, Next one is a 2-bit magnitude comparator. A comparator used to compare two binary numbers. Each of 2 bits is called as a 2-bit magnitude comparator. It consists of 4 inputs and 3 outputs to generate less than, equal to, and greater than between the two binary numbers. So this is the truth table of a 2-bit magnitude comparator. Since it's a 2-bit magnitude comparator, for A input we have 2 bits A1, A0, and for B input we have 2 bits B1 and B0. So since it has 4 inputs, you'll be having 16 combinations. And as usual, you'll be having 3 outputs, A less than B, A equal to B, and A greater than B. So based on the inputs, it will be comparing each bit and it will be producing the output as mentioned in the 1-bit magnitude comparator. So the Karnaugh map is drawn for each of the output A less than B, A equal to B, and A greater than B as shown here, and you'll be getting the output expressions. So for A less than B, you have three groups. One is four ones grouped together at the right top corner, and next one is in the middle. Two ones are grouped as two ones together, and top one and bottom one is grouped as another group. So you'll be getting the following expression: a1 bar b1 plus a1 bar a0 bar b0 plus a0 bar b1 b0. The second Karnaugh map for A is equal to B. You cannot group anyone, so you'll be keeping all the ones separately, and you'll be having the expression as shown here. And for A greater than B, again the grouping is as shown here, and you'll be getting the expression A1 B1 bar plus A0 B1 bar B0 bar plus A1 A0 B0 bar. So the logic diagram is implemented for all these three expressions using NOT gate, AND gate, and XNOR gate and OR gate as shown here. Some of the applications of magnitude comparator are: it is used in central processing units and microcontrollers, and also it's used in control applications in which the binary numbers representing physical variables such as temperature, position, etc. are compared with a reference value. It is also used as process controllers and for servo motor control. It is used in password verification and biometric applications. Let us take up some assessment questions. One that is not the outcome of a magnitude comparator is dash. The answer is A greater than B, A minus B, A less than B, and A equal to B. So the answer is A minus B. If two numbers are not equal, then binary variable will be, the options are 0, 1, A and B. Yes, the answer is 0. How many inputs are required for a digital comparator? The options are 1, 2, 3, 4. Yes, the answer is 2. So two numbers will be compared and you'll be getting the three outputs. Thank you for watching this video.